We're thinking about hitting times of Markov chains right now. That is, we have a discrete filtration of our probability space and a state space S, a Markov chain xn, taking values in that state space, indexed by all possible start distributions but with a fixed transition kernel as usual. Then the hitting time tb is the random variable associated to x, which is the smallest time, including 0, at which xn is in B, where B is some measurable subset of the state space. And we define this to be infinity if xn is never in B. So Tn is a random variable that takes values in the natural numbers together with plus infinity. We'd like to understand what we can about the distribution of this hitting time Tb, and two quantities that we will usually be able to say something meaningful about are the probability that it is finite, given some initial point x for the process, and the expected value. Now, of course, if this quantity is not 1, if there is some positive probability that the Markov chain never hits B, starting in state x, then this expectation will of course be infinite because it will be a sum including that small positive probability times infinity. However, it's possible for this to be infinite even if this probability is 1, as we saw in the last lecture for symmetric simple random walk on the integer lattice, which is null recurrent. It's recurrent because this probability is 1 for every x, and every state B, if B is just a singleton state, but this expectation is infinity for any singleton state B. In this lecture, we're going to generalize the kinds of quantities related to the hitting time that we can analyze and develop a generic tool similar to what we used in the analysis of symmetric simple random walk, which is called first step analysis, in order to attack them. Here are the two kinds of examples that we'll be able to handle in this framework, and then we'll later see how those can tell us a lot about questions involving TB for different kinds of sets B. For example, we might be interested in the expected value of some function of the hitting location, x of TB. Of course, if we could study this expectation for every bounded measurable function h, then that would give us a complete description of the distribution of the hitting location. We will probably study it for a particular h, but it will work as well for any h as any other. We should be careful, though, because if TB is infinite, then this doesn't even make sense. So to be more precise, we're going to study the expected value of this on the event that TB is finite. And for example, if we take h to be the constant function 1, then that just gives us the expected value of the indicator of the set where TB is finite. In other words, included in this case is the probability that TB is finite, which is one of the quantities we'd always like to compute. Now, it's often useful to give meaning to quantities like this in terms of some kind of economic games or gambling games. So here we can think about it this way. You start at some state x, and then you execute the Markov chain randomly moving from state to state until you hit B. At that point, you'll hit B. At some point y, you will collect a certain amount of money. That's what h represents. It's the reward for hitting the set B at the location y. And then we're faced with a question. If I enter the set B over here at this location, I might collect a certain amount of money, but if I hit at another location, there might be a negative number there. I might owe money to enter. And the question is, should I even play this game? Well, the baseline answer to that should be given by the expected value. Are you expected to at least break even when you play this game, or are you expected to lose money? That determines whether or not you should play from the beginning. So that's one reason we might want to compute this kind of quantity. Similarly, we might want to take the expectation of a sum like this. That is, we start at some state x and we follow along the Markov chain until we enter B, but at each step along the way, we collect some money, g. In this case, since this sum could be infinite, if tb is allowed to be infinite or at least unbounded, we'd better be sure that g is a positive number. And to be clear, in this case, g is a function of the state. It doesn't also depend on the time n. Therefore, if we double back and hit a state a second time, we collect that money again. It's replenished right away in this version of the game. And this quantity inside here is going to be the total amount of money that we collect along the path until we get to b. We are interested in how much I should expect to collect based on this function until I enter b. We're going to present a general framework for computing, or at least starting the computation of quantities like this, using the first step analysis of the Markov chain. In order to do that efficiently, we need to introduce a little bit of new notation, because the quantities involved will be some restrictions of the transition kernel, and those are no longer probability kernels, those are sub-probability kernels. So if I have the same setup as before, I have a state space S, which is a measurable space with a sigma field B, and I fix any measurable set B, we can restrict the sigma fields to that set B. We've seen this before. Scripty B restricted to B is a new sigma field consisting of the set of all elements of the original sigma field, all measurable sets, that were subsets of B to start with. Now you can write this in another way. You can also think of it as the intersections of all sets in Scripty B with that one set B. And the fact that those two are equal is always true when you have a field, as you can easily work out. Since B is a sigma field, you can check quickly that this is a new sigma field over the new universe B instead of omega that we started with before. Now, if we have a probability kernel defined on this measurable space to start with, we can restrict it to B and the restriction of the sigma field. That is to say, this new restricted probability kernel is at a point x in B and a subset E in Scripty B just equal to Q of x. And that subset which doesn't look very interesting. We're just restricting it, of course. But if we're going to be pedantic and careful about this, then we should note from this right away that one problem, which is not a big problem in the end as long as we're careful, is that if we integrate this kernel for any fixed x, what we get is, of course, Q of x and B. Now that is not necessarily equal to 1. In the general case where the B was all of S, the definition of a probability kernel included the statement that Q of x and S is constantly equal to 1 for every x. But this is not equal to 1. It's less than or equal to 1, but it's not necessarily constant either. This is just some function of x, measurable and less than or equal to 1. That's a sub-probability kernel. Now, if we have a sub-probability kernel like this, we can, as usual, identify it with an integral operator on the space of bounded functions on the original measure space. That is, we have capital Q sub B is an operator here, which does exactly what the old one did, except we're integrating with respect to the restricted kernel. And the restricted kernel is only defined on the set B, so this is an integral over B. In other words, we could write this just as the original transition operator Q applied not to the function f, but to the restricted function f times the indicator of B. Now let me also note, because this will be important, that we could also think of this QB acting on non-negative measurable functions. We don't have to apply it only to bounded functions, although that is usually the setting in which we've seen it. We will be integrating non-negative functions, and there's no trouble doing that. We just need to avoid possibly adding plus and minus infinity if we're not dealing with bounded functions. Now, let's note a quick decomposition here. How does the restricted kernel QB relate to the original? Well, because B and B complement form a partition of the whole space omega, it's easy to see that the probability kernel Q decomposes as QB plus Q B complement. And that means that the operator Q, thought of as acting on functions over the whole space, decomposes as Q restricted to B plus Q restricted to B complement. We'll make frequent use of those easy decompositions. And let me note, which we can see easily from here, that this operator QB, it has pretty much all the same regularity properties of the original operator Q. It's going to be monotone, for example, which we will use. The only exception is that QB of 1 is no longer Q of 1, it's Q of the indicator function of B, and that's not necessarily equal to 1. It's just some new function that is less than or equal to 1, which is a restatement of what we saw right here. So with that notation under our belt, we can now state a generalization of the kind of recursion that we got from first step analysis in the random walk example to generally compute the quantity that we were interested in the first example on the first slide. That is, if we take a bounded measurable function h, or a measurable non-negative function h, which could even be allowed to take infinite values, and xn is a Markov process whose transition kernel is Q. If we have any measurable subset B of the state space, then we can consider this quantity here. Starting at x, what is the expected value of h of the hitting location of B under the event that the hitting time is actually finite? This defines a function u of x defined on all x in the state space. The conclusion that we'll draw from first step analysis is that if h is a bounded function, then so is u. If h is a non-negative function, then so is u. And in either case, u is a solution of this fixed point equation. U is equal to QU on the complement of the set B. Whereas on the set B, u is just equal to h. For that second statement, that's pretty clear. It's just because if x is in B, that means that the hitting time of B is 0, which of course is less than infinity. So that means that this condition is satisfied, and TB is 0, so this is just going to be h of x0. Which, under the condition here, is h of x, which is what is claimed in this case. In the case where we start outside of B and we get this fixed point equation, we just decompose Q as QB plus Q complement, and note that therefore that means that on B complement, U is a solution of this equation here. U is the restricted transition operator QB complement applied to U, plus this constant function, QB applied to the input function H. To be clear about what that means, what this is saying is that for every x outside of B, U of x can be computed by integrating the kernel Q against the function H on B, and then adding this recursive term, the integral over B complement of the kernel against U. Now, in particular, if we take h constantly equal to 1, where we know in that case u of x is the probability starting in x that the hitting time of B is finite, then what this tells us is that u is a solution of the fixed point equation. U is QB complement of u plus QB of the constant function 1, which again is not equal to 1. It's equal to Q applied to the indicator function of B on B complement, whereas u is constantly equal to 1 on B. And that last statement is a special case of what we wrote over here, and also clear because if we start in B, then the hitting time of B is 0, which is for sure finite. Okay, let's prove this. we're going to use the first step analysis, which, remember, tells us that if we have some function f of the paths of the process, then the expected value of f of the whole chain starting in x can be computed by taking the expected value starting in any state y of f of the chain first starting with x and then continuing with the chain as it started before, and then integrating that over the whole state space q of x dy, where q is the full transition kernel. So in this case, we're going to be taking that function f to have this form here. We already noted in the last lecture that the hitting time is such a function of the path, and so therefore also is the indicator function of the event that hitting time is finite. It's a 0,1 valued function of the path. And then we're multiplying that by this function here, which is a composition of functions of the path. TB is a function of the path, and x sub n is of course a function of the path. So we compose those and then compose those with this measurable function, and altogether we get a measurable function of the path. Now it's useful to write this xtb as lb, as we did last time, the hitting location of b. And the reason is that, as we argued last time, purely deterministically on paths, if we start at a point x that is outside the path, then the hitting location of a path that starts with some point x, which is outside of b, continuing with other terms in the path, then that's the same as the hitting location if we discard that initial entry, since we didn't hit at x, and so the hitting location happens somewhere later. Also, if we start the path at x and then ask whether we ever hit b, that's the same thing as starting the path one step later and asking whether we ever hit b. If this is infinite, we can't make it finite by starting one step later. Whereas if this is finite, then this is going to be one step sooner and is still finite. So putting those two things together, what we see is that this function of the path is invariant under adding or removing an initial term. That is, f at little x and then the path is the same as f at just the path. And therefore, from our first step analysis, we get that the function u of x, which is this expectation here, it's the expected value of this function of the path starting at x, is this term here, integrating over all states y. But as we just noted, this integrand here doesn't care about that initial x. And so that's the integral of this. But this expectation inside here, that is u of y. And so what we get is the integral over s of q of x dy u of y, which is exactly the statement that u is equal to qu of x. Again, all of this in the case where x is in B complement. And finally, let's use the decomposition of q. That's qb complement of u at x plus qb of u at x. And that second term there, well, by definition, that's the integral of q of x dy integrated against u of y over b. And if y is in b, we know that u of y is equal to h of y. And so this second term here is just qb of h of x. And that tells us that qu of x is equal to qb complement u of x plus qb of h at x. And that gives us exactly the recursion for u on B complement that was the second statement of the theorem. The first statement that u is equal to h on B was proved basically in the statement on the last slide. And so that concludes the proof of this theorem. We can do a very similar first step analysis to handle computations of the second kind that we did. If g is a non-negative function defined actually only on B complement, because we're never going to use its value on b, since when we enter b we'll stop the sum. And if we define v at x to be the expected value starting in x of the sum of g of xn, where n ranges up to but not including tb, we stop when we reach the boundary of b, then v is just the zero function on b, which is just because this is an empty sum if x is in b. And if we start at a point x in b complement, then v solves this recursion. V is qv plus g, which we could also write, because we're starting in b complement, as q restricted to b complement of v plus g. Now in particular, this also allows us to compute the expected value of the hitting time, because if we take g to equal the constant function 1, I guess on b complement is all we care about, then these terms here will all be 1, and we're just adding up 1 tb times. This sum goes up to but not including tb, but it starts at 0. And so we get that here v is equal to the expected value starting at point x of tb, which could of course be infinite. And if we specialize this recursion to that case, what we get is the following equation for computing the expected value of the hitting time. For every x in b complement, v of x, which is the expected value of tb, is qb complement v at x plus 1, which is the integral over b complement of q of x dy, expected value of the hitting time started at y plus 1. So let's just quickly run through the proof. Here we're taking our function f of the path to be this sum here, and that is of course manifestly a function of the path. It's this function of the terms in the path up to some potentially infinite stage, and the stage where we stop is this time here, which we know to be a function of the path. So this is a function of the path. And in this case, we want to use first step analysis. We just need to see how this function behaves under adding a new deterministic initial term, little x, to the path. So if I take f of little x and then the rest of the process, well, if that original initial term x naught happens to be in b, then this sum will have, when n equals 0, g of little x, and then the rest of the terms will not be present. So that will equal g of x, whereas if x naught is not in b, then we will have some more terms in the sequence. In fact, we'll have exactly all of the terms in the sequence after the little x until we stop at tb. So in that case, this is g of x plus f of the original path. So that is altogether, and this mirrors exactly what we stated 2 lectures ago as a general rule for how to handle these kinds of functions of paths. This is g of little x plus the indicator that x naught is in b complement times f of the original path. And that means that when we do the first step analysis, v of x being this expectation here will equal the integral over all states y of this appended path function here. But now we can use this formula for that appended path function inside there and write this as g of x, since the expected value of the constant g of x is g of x, plus the integral over s, q of x dy, times the expected value starting at y of the indicator that x naught is in b complement times f of the original path. Now in this integral, we're integrating over all y's, but we have this indicator function here. And so since we're going to be substituting in y for x naught, if we start with a y that is in b, then this whole term here will just be 0. What that means is that we can forget about this and we just integrate over b complement. But we then see that since this is f of the original path here, that just amounts exactly to g of x plus q restricted to b complement of the function v at x. And then finally, we just need to note that since v is identically 0 on b, this integral here, which is q of v times the indicator of b complement, and since v is equal to 0 on b, v times the indicator of b complement is just v. And so that concludes the proof of the desired statement here. So, to summarize, if we want to compute these two kinds of expectations which generalize the probability that the hitting time is finite and the expected value of the hitting time, u and v, can always be calculated by these kinds of recursions, where we have the boundary conditions, if you like, that u is equal to h on b and v is equal to 0 on b. Now, if we're being hand-wavy about this, we can solve these recursions like this. U will be I minus the operator QB complement inverse applied to QBH. And V will be equal to I minus QB complement inverse applied to G on B complement. Since we know what they are on B as well, that gives us a complete, easy description of how to solve for U and V. The problem is that that presupposes that this operator here is an invertible operator in some sense. And the fact of the matter is that it frequently is not. So there will often be more than one solution here. Now, there is one nice case where it turns out that it is an invertible operator, and that is if for every x in B complement, the probability starting at x that the hitting time of B is finite is 1. This is the most favorable situation, and we're going to look at some conditions to make this true in an upcoming lecture. But there are interesting cases, for example, one that we'll see in the next lecture, in which this is just false, and in fact, this operator is just not invertible. In that case, if we want a complete general story here, we would need to prove the following theorem. That in these two problems that we've considered here, where u and v are solutions of these recursions, if there's more than one potential solution with the given boundary conditions, then the one that we're interested in, the one that solves the original probabilistic problem, is the unique minimal solution. That is to say, if there will be a bunch of different solutions, then there will be exactly one of them that point by point is less than or equal to any of the others. And that minimal solution, which is unique, will be the solution to the probabilistic problem. We're not going to take the time to prove this, but if you're interested in the details, you can see section 22.8 of Driver's Notes. Some of the aspects of that theorem will come up in the next few lectures. Next time, we're going to see how to apply the tools that we developed here using first-step analysis to completely understand the behavior of biased random walks.